In this particular tutorial, we are going to discuss about astronomy and cosmology, a topic in A-level physics. That's Cambridge 9702. If you are new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload another tutorial, you'll be notified. In Proflan YouTube channel, I do maths and physics. So if you are taking a Dexel Cambridge, this place is for you. So let's dive in so that we can see what are the key areas, most important subtopic and key concepts that you must know as far as you are doing A-level physics. Astronomy, first I need to give you just an introduction of what we are going to deal with here. Astronomy deals with celestial objects in space, study of stars, how they are born, how they evolve, and how they are actually transformed. Because there is a formation of a star is formed when nebula and dust particles are drawn together due to gravity. They are compressed, then there will be nuclear reaction which will start, and then it becomes a protostar. And in the process, the star will undergo different transformation to become a main sequence, become a red giant star, and eventually the star can become a star can be transformed to become a black dwarf and a white dwarf, and eventually it dies off. So for astronomy, that's where you study evolution of stars. But when it comes to cosmology, this is where you study the origin of the universe. Where did the universe originated from, and what are the theories involved to the origin of the universe? Because there are different theories that try to explain the origin of the universe, and because of different religious inclinations, we have different theories that explain how the universe originated. But now in A-level physics, you are going to base your discussion on Big Bang theory. In cosmology, we shall study Big Bang theory. We just check what are the evidences that indeed confirms that the universe might have originated from Big Bang theory. So basically that's what we're going to discuss in this particular topic. However, the first thing that you need to understand that when we look at stars in the sky at night, we really observe that some stars are brighter and other stars are dim. So what determines the brightness of the stars and what we see is the nuclear reactions that are taking place inside that particular star. So if a star is fusing hydrogen and hydrogen, and another star is fusing helium and helium, the star that is fusing helium tend to produce a lot of energy, so that star will be brighter. But sometimes a star may be dim when we are observing it from Earth because the star is very far, and another star may look brighter but because it's close to us. So those are some of the aspects that you really need to understand in this particular topic. The concept that also you must understand is the concept of luminosity. You need to understand how to define luminosity. And we're going to say in simple terms that luminosity is the total power emitted or radiated from a star. A total power radiated from a star is what we call luminosity. The greater the luminosity, the more bright that star may become. And also we need to understand that the unit for luminosity is watts or joules per second. So that is some of the concept that you have to understand. And you need to realize that as the distance increases, the luminosity decreases. Radiant flux intensity is the quantity that is obtained by luminosity divided by the surface area or total surface area of a star. So remember, a star is in a form of a sphere. So in order to find the surface area of a sphere, we're going to use the formula 4 pi r squared. So in that case, you can see now we are using this value here, this formula here. The formula imply surface area of the star, and this d, yeah, if you are measuring flux intensity from Earth, you'll have to use d. D is the distance from the center of the star to where you are measuring the radiant flux intensity from. So radiant intensity is a quantity that can be measured from Earth. There is a device can be used to measure radiant flux intensity of a distant star, and the distance d that we are having here is the distance from where the person is measuring the radiant flux intensity to where the center of the star. So as the distance increases, the radiant flux intensity also keep on increasing, and then for that reason, as the distance increases, the brightness of a star decreases, right? So upon looking at that, you need also to understand the unit for radiant flux intensity is watt per meter squared. And next we need to understand that this actually it applies all, it follows the inverse square law. As the distance increases, the radiant flux intensity decreases. Now, in the process of measuring distance of stars, and we are going to use the concept of standard candles. Standard candles are type of objects. Standard candles are type of object whose luminosity is known. Standard candle is a device, is an object, a celestial object whose luminosity is known. So if you know the luminosity, you can be able to determine how far this object is from where you are. Now, if astronomers want to measure the distance of a star, what they need to check, because these stars, they coexist in clusters, they exist as groups. So we have a collection of billions of stars together, and within those stars, we may, in that collection of stars, we may have now a standard candle. A standard candle may include a supernova. A standard candle may also include a Cepheid variable. Yeah, a Cepheid variable is a type of star which keep on pulsating, increasing the brightness, and the brightness keep on increasing and decreasing. And these Cepheid variables, they can be used as standard candles. Now, since you know the luminosity of the standard candle, and this standard candle is in the galaxy of a collection of stars, right, then meaning that you can be able to measure the radiant flux intensity. So if you can measure the radiant flux intensity, you can then go ahead, say distance is equals to luminosity over 4 pi f. So that is how astronomers manage to determine the distance of different distant galaxies. Yeah, actually, right now I'm trying to also scan some of the questions that have been tested before, so that I'm going to show you how you are going to use standard candles, how questions are asked when you are asked to state how to use the standard candle to determine the distance of a star. All right, so we need also to mention that finding stellar radius, that is the radius of stars, we are going to use the concept of Wien's displacement. But Wien's displacement law is a law that relates maximum amplitude. This is the maximum wavelength rather, and this is the wavelength of the maximum intensity. So because different stars produce light in the entire spectrum, so but for that particular star there is a type of wavelength which will give the maximum intensity. So you can be able to read that wavelength here. Yeah, This is the wavelength that will give maximum intensity. And wavelength, maximum wavelength and temperature are related. They are inversely proportional. So if you know the wavelength, you can be able to determine the surface temperature of a star. So maximum wavelength is inversely proportional to the temperature. And in that case, now we have Wien's displacement law. And this is the type of law that can enable you to find the surface temperature when you know the wavelength. Okay, so B is the Wien's displacement constant, which is approximately 2.8 times 10 raised power 2.898 times 10 raised power -3 meter Kelvin. And we can be able to apply that. You can be able to answer different examples I've tried to work out there. And you can see hotter stars appear to be blue, and those stars which are cooler, they appear to be red or yellow. Yeah, so I'm gonna see how we can be able to use this concept in the next few seconds, so that we can be able to get well prepared for the exam. Okay, there is another law that you must know, which is called Stefan-Boltzmann law. And this is a law that tries to relate the radius of a star and temperature and luminosity. And luminosity of the star is the total energy emitted per second. And we also said is the total power emitted by a star. But luminosity increases as area increases. If the area is large, there will be greater luminosity. So meaning that luminosity is directly proportional to the surface area of the star. And then we have the surface temperature. If the surface temperature of a star is high, then it means that luminosity also will be higher. So Stefan-Boltzmann law is relating radius or surface area and temperature of a star. And this is the formula where L is the luminosity radius, R is the radius, T is the surface temperature in Kelvin. But remember, this is raised to power 4. And then also we have Stefan-Boltzmann constants. And guys, don't confuse that with Boltzmann constant, which was we were looking at ideal gases. All right, so these are examples where you can be able to determine the surface temperature for the sun, whose luminosity is this, and the radius is given here. You can be able to apply the formula in order for you to get the answers. Now, after that, we are now going into cosmology. And cosmology, we shall base our discussion on concept of Big Bang theory, whereby according to Big Bang theory, it's believed that the universe originated from a single dense point, which expanded to become what we have right now. As it's being observed that distant galaxies are receding from each other, they are moving away from each other because the space between them is increasing, then that serves as a proof that the universe might have originated from Big Bang theory, because even right now the universe is expanding. And also, what also confirmed that the universe is expanding is the redshift that is observed from distant galaxies. As galaxies are moving away, then light emitted from the surface of stars display a redshift. They become stretched due to Doppler effect. So redshift is a phenomenon where spectral lines from distant galaxies are shifted towards the red section of the spectral line. And this redshift now confirms that the universe is what? Expanding. You need also to understand how Hubble's law states. Hubble's law said that the speed at which galaxies are moving away from each other is directly proportional to the distance between them. So in that case, this now equation that we have here, V is equals to H naught D, is now what we call Hubble's law, where H naught is Hubble's constant. And if you plot a graph of V against D of a star, you are going to get a straight line. And the gradient of the line will enable you find the Hubble's constant. This Hubble's constant is also used to determine the age of the universe. Of course, we can be able to determine the age of the universe by saying age of the universe is equals to 1 over Hubble's constant. You just take 1 divided by Hubble's constant, and you get that the universe might have been formed about 14 billion years ago. Also, take note of this formula that we are having here for galaxies. For light emitted from galaxies, when the wavelength is observed, change in wavelength is going to be related by the speed of the galaxy as follows. Change in wavelength over the wavelength is equals to change in frequency over frequency, or that can also be equals to speed of the galaxy over the speed of light. And usually the wavelength that you usually put at the bottom is the wavelength. This the smaller wavelength is the smaller wavelength, because when you are finding change in wavelength for a redshift, there's a larger wavelength minus a smaller wavelength, because light has undergone redshift. So meaning the wavelength increases, the wavelength of light increases. Observed wavelength is usually larger than the actual wavelength of light that is emitted. So due to Doppler effect, wavelength will be higher. So you take the higher value minus the smaller value, and then the smaller value definitely most of the time for redshift will be below here. So having looked at that, we need also to understand the evidence of Big Bang theory. One of them is the redshift, which is observed from distant galaxies. And then we also need to mention that the universe still displays a few things like phenomenon of the presence of CMBR, microwave background radiations, which are available. So everywhere and stretching in all direction, there is microwave background radiations everywhere on Earth. So which means that they might have been produced during Big Bang. That's why they are everywhere. Yeah. Another one is the temperature of the universe, meaning that as the universe expand, the temperature of the universe has cooled to whatever temperature we have at this particular time. Now, this moment, what I want us to do is actually to look at different questions that have been tested in different exams, so that you can be able to see how are you going to answer questions, and how are questions usually asked as far as this topic is concerned. Just give me a second so that I can be able to now finish the scanning of those questions, so that I can be able to display them here. We continue looking at them. And if you are new to ProfLearn YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. You can be able to access all the PDF that we have here in our Patreon page, and also you can be able to access them in my TES shop, whereby you can be able to upload them. You can be able to download them. I usually upload even my handwritten notes. Yeah, these notes that you can see here, the notes that I'm having at this point here, you can be able to access them in our Patreon page. All these notes that you can see I'm displaying, you can be able to access them. I've tried to make them simple and easy to read. Guys, you can be able to check in our Patreon page. Just download them, have them in your computer, so that you can be able to you can be able to continue with your revision. All the best, guys. Let's now dive in and get to see the kind of questions that have been asked in different exams, so that we can be able to prepare well for these exams. Yeah, guys, if you have not subscribed to Provlan YouTube channel, just subscribe so that you can be able to help me grow this channel, and at the same time we can be able to reach more students. This is the only support that you can be providing me by subscribing, and then we can be able to grow the channel together. Well, let's now, I think it's almost done. So for us to look at those questions and see how are you supposed to approach them, how are you supposed to do them, because the best way to prepare for A-level physics is understanding the concept that is asked, understanding the topics that are you deal with, and then once you've done that, what follows is now the application of the concept, so that you can be able to confirm you've understood. Yeah. Okay, so I think we are good to go. Yeah, so the questions are here. The questions are here for cosmology. Yeah, so this is different questions that have been tested before as far as this topic is concerned. Now let's dive in so that we can be able to see how are you supposed to answer A-level physics, astronomy and cosmology concepts, and what is the best practice that will enable you to earn the mark. Now let's see the first question. The first question was testing 1. Now looking at this question here, we are given a question where you are expected to state what's meant by the term luminosity of a star. What do we mean by the term luminosity of a star? From our notes, I've mentioned that luminosity of a star is basically the total power of radiation emitted by a star. Is the total power emitted by a star. Now, once you've understood about luminosity of a star, you must also understand how you can be able to use a standard candle. You need to understand also how we can be able to use a standard candle to determine the distance of a galaxy. So the first thing also we mentioned at this particular point, we say that a standard candle is an object whose luminosity is known. So if you know the luminosity, then you can be able to measure the radiant flux intensity from Earth, right? So the first thing that we need to identify when you are trying to explain how standard candles are used to measure or determine distance of galaxies is that you need to ascertain, you need to tell that the luminosity of a standard candle is known, then the radiant flux intensity F is measured from Earth. It's a quantity that can be measured, but you cannot measure luminosity. No, what you can measure is radiant flux intensity. Then in order, once you have radiant flux intensity and you know the luminosity of the star, then it means that now you can be able to go ahead and find what we call the distance, and distance is going to be equals to L over square root of L of 4 pi F. Okay, right. So once we've done that, let's now dive into the next part. We are being told there is a spinning star here. The sun rotates on its axis, it's spinning on its axis around there. And where is this question? This question for on this page. Where is this question? Did I miss putting there? Yeah, so what I need to do is immediately to add. I need to add that page. I think that page is missing. I don't know how come the page missed there. Maybe I didn't realize that I did not scan that. Let me just include that page so that we can be able to see what that question was asking. Yeah, so before that, we'll continue with the next bit, then we come back to look at it. Now, looking at the next question where you are asked to state Hubble's law. So we are going to say that Hubble's law states that the speed at which galaxies are moving away is directly proportional to the distance from the observer. So basically the recession speed. The recession speed means speed at which a galaxy is moving away. Okay, that's what we mean by the recession speed. Yeah, I think this is done. Yeah, so let me just bring in that question there. Yeah, so this is the question that we are talking about, where the sun is spinning on its axis, and then we are given the observed wavelength at point X and the observed wavelength at point Y. We were supposed to work out what the sun rotates with the period of this, show that the radius of the sun is approximately this value. So the first thing that we were to realize is that we are going to use the formula V is equals to 2 pi r over t, because this is the orbital rate or orbital speed of a rotating object in its orbit. But also we can be able to use, because since the sun is rotating within the axis, so how long does it take to make one complete rotation? The time given there is the time taken for it to make one complete rotation. So if you know the period, we can be able to work out the radius, and the velocity or the speed at which it's spinning can be obtained from this formula that we are having here. Yeah, the formula due to Doppler effect. Yeah, because already we have the velocity, the wavelength, and also the wavelength in Y. So since these objects are moving in different ways, one point X is moving the other direction and Y is moving the other direction, then we are going to have one point moving away and another point moving towards. Then in that way we are going to have a change in wavelength. One section will have a red shift, another section will have a blue shift. So in that way we can now apply the Doppler formulas that we have there, so that we can be able to get the speed of at which it's spinning. So in that way, you say that change in wavelength over wavelength is equals to speed at which it's spinning over the speed of light. And that is exactly what I did here in order to get the speed at which it's spinning to be 2102.8. So once you have done that, now you can be able to use that speed here together with the period and 2 pi, and the radius now is going to be 6.93 times 10 raised to power 8. State and explain how the expected wavelength of light observed from Z compares with the emitted wavelength. So Z is moving towards the Earth, so the observed wavelength is going to be less than the emitted due to a redshift. This is the case due to a redshift. So basically that's what we explain. And also, if you are asked to work out the luminosity of the sun, you need to understand you are using Stefan-Boltzmann law at this point. And since we already have the radius, we have all the variables, then we can be able to make T the subject of the formula. This is the fourth root, so it will be luminosity over 4 pi r squared, and Boltzmann constant, Stefan-Boltzmann constant. Here we can be able to get our answer as 5800 Kelvin. So basically that's what was tested in Web March 2025. Now let's dive in and get to see in the other years. So that's where in the following year there was also a question on stating Hubble's law, and we're going to say that Hubble's law is states that the recession speed at which a galaxy is moving away is directly proportional to its distance from the observer. And we are also supposed to explain why the observed wavelength and the emitted wavelength have different values. So we need to realize that the galaxy is moving away from the Earth, so the observed wavelength is longer or is redshifted due to Doppler effect. Next, you are supposed to calculate the speed of the galaxy. So for you to calculate the speed of the galaxy, you are going to use this formula here, whereby we said that change in wavelength is going to be the larger wavelength minus the smaller wavelength. So we shall take this wavelength, we subtract this, and then times the speed of light, because from here this is the speed of the star at which it's moving. So if you make V the subject, you are going to have our equation well seated here, which you are going to substitute, and you will get nothing other than 1.9 times 10 raised power 7. Explain how the temperature determined using observed wavelength compares with the true value. Observed wavelength has a larger value, because it has been redshifted. So if the wavelength is larger, then the intensity will be lower, yeah, because here we are using Wein's displacement law, because we said maximum wavelength is equals to 1 over T. So here, if we make T the subject, we can be able to say T is equals to 1 over maximum wavelength. So which means that if the observed wavelength is longer, then it means the temperature will be lower from Wein's displacement law. So that is the concept we are going to use at that particular point. Next, also, we are asked to use the answer to determine the distance of the galaxy from the star. So we can be able to use the speed that we have obtained and Hubble's constant in order to do that, because distance is going to be speed of the galaxy divided by Hubble's constant. So that's some of the questions that have been asked, and that is how you are supposed to approach them. We have also a question whereby you are told that the sun has a surface temperature of 57.8 Kelvin, and the luminosity of the sun is 3.85 times 10 raised to power 26 watts. Now you are supposed to calculate the radius of the earth, in this of the sun rather, in this case, you are supposed to use Stefan-Boltzmann law, which is L is equal to 4 pi r squared, Stefan-Boltzmann constant times temperature raised to power 4, T raised to power 4. So if you make out the subject, you are going to get your answer here being equivalent to 7.0 times 10 power 8. And in order to work out the radiant flux intensity, we are going to use the distance that is being provided. And we know radiant flux intensity is given luminosity over 4 pi d squared. So our d squared here, the d we have here is the distance where the distance between the observer and where the star is, and the center of the star in that case. So in that case, we're going to calculate the radiant flux intensity using this formula. And if you substitute the quantities, because this is our d, and we have the luminosity provided in the question from the previous section, then we can be able to go ahead to work it out. And anytime you are told to draw the variation, the star which has the same radius but lower temperature, when it has a lower temperature means it has a larger wavelength. So this one is smaller wavelength, this highest correspond to a smaller wavelength. So if it has lower temperature, it must have a longer wavelength according to Wien's displacement law. Is B over T. B over T. Yeah, so basically that's what you are supposed to. Even a much lower temperature will behave like that. Yeah, so a much lower temperature. All these waves or all these waveforms will be below each other. So as temperature keeps on decreasing, the wavelength will be longer. Yeah, so and all this we've mentioned them. I've actually included all that in our notes, so you can be able to easily remember. So make sure you've checked in our Patreon page, whereby you can be able to download these particular notes that I was able to prepare for you, so that you can be able to prepare for the exam. And if you are new to Proflan YouTube channel, consider subscribing, so that anytime I'm going to upload more tutorials, you'll be notified. So let's dive in into the next part of the question that were tested, so that we can be able to see what are the main questions. We are told the galaxies in the constellation Corona Borealis is moving away from Earth. So if it's moving away from Earth, its light is going to be shifted. It's going to undergo what we call a redshift. So in that process, all these lines, spectral lines we are having here, will be shifted equal distances towards the red side. And remember, the red side is the one that's having a longer wavelength. So basically, that's why we have that. Then the galaxy in Corona is moving away from the Earth at this particular speed. Use the information to calculate in meters the observed wavelength of the lowest visible energy. Remember, the lowest visible energy is going to correspond to the longest wavelength. So that is the most important area that you had to remember. So we are going to take the wavelength we shall use in this particular question will be 656. And the reason as to why we are using 656 is because the lowest energy is going to correspond to the longest wavelength. So in that way, we shall be able to say now change in wavelength is going to be equals to, because we know change in wavelength, let me just move the slide properly so that you can be able to see here. So what I'm trying to say is that is that change in wavelength over wavelength is equals to V over C. So our wavelength, the observed wavelength, will be, of course, redshifted, but the wavelength, the real wavelength of light emitted from the sun of that particular galaxy or that star is going to be 656. So that's the value we shall be putting below here. So now with that, if you make change in wavelength subject, you are going to take 256 times the speed of the galaxy that is given over speed of light. That's going to give us the change in wavelength. So if we want to find the change in wavelength, we'll take this wavelength times the speed of the galaxy over c. But remember, this speed was given in kilometer per second. You had to change that by multiplying by 1000. So it will be 21,400 000 times 656 over 3 times 10 to the power 8. Change in wavelength is that. So how do we get change in wavelength? Is the observed wavelength minus the actual wavelength of the light should be equal to the change in wavelength, which we had gotten here. If you work it out, you are going to get your answer being 703. So that becomes the answer for that particular point. And we are supposed to explain whether this value state and explain whether this value of temperature is too high or too low. Because the wavelength is actually high, then the temperature is going to be low. So increase in wavelength decreases temperature. And then we also have a question to do with what's the measure of luminosity. We have mentioned that is the total power radiated by the star. And also there is a question how a standard candle can be used to measure determine the distance between the galaxy and the observer. We have to mention that the standard candle, the first mark will be awarded when you say the standard candle is an object of non-luminosity. Then also another mark will be awarded when you mention that radiant flux intensity is measured. And then the last mark will be awarded where you'll be writing this particular formula. So that's exactly what you are going to mention and for you to earn all your marks. So at this particular point, I want you can be able to go through this. And I need also to look at explain how the redshift lead to idea that the universe is expanding. So because all the galaxies display a redshift, meaning they're moving away. If there is a redshift, it means these objects are moving away from each other. Now, since the distance between the observer and the galaxies is increasing, ever increasing, then it means that the universe is expanding. So how do we put that? We are going to say light from distant galaxies shows redshift, meaning the wavelength is increased compared to the light produced in the laboratory. This redshift is caused by Doppler effect, which occur when a source of a wave is moving away from us. So when a source is moving away, you will see a redshift. But if the source is approaching, you will see a blue shift. Now, since all the galaxies display a redshift, it means that they are moving away from each other, and that could be as the universe is expanding. So basically, that's what you need to understand as far as astronomy and cosmology is concerned for A-level physics. And if you are asked to sketch a graph of V against D, and then you realize that for galaxies, you need to realize that it should be a straight line, and the gradient represents Hubble's constant. So up to that point, we shall stop there, and I wish you guys all the best. If you're new to Proflan YouTube channel, consider subscribing so that anytime I'm going to upload more tutorials, you'll be notified. See you the next tutorial.